Okay, hello everybody. We are going to continue from what we had in the previous class, and remembering that our topic was a truss structure, and we're supposed to solve particularly the 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 uh, the the member forces of a truss structure. And at the end of the previous class, we've been trying to solve this truss structure shown here. That given that we have uh, joints A, B, C, D, E, and at point E we have a external force of 100 pounds that is going downward, and we have the structure dimension that given. Okay, so we first draw the free body diagram of the entire structure, and then we can solve all the unknown support forces here. Okay, and then we started to perform the method joint, right? Then we started to perform the method joint. It is repeatedly precise for the force analysis for each of the joint here. And remembering that we will also be talking about, we should analyze which of the joints here. It should be those joints that with no more than two unknowns. Okay, typically we started from the edge of the structure, particularly for the if you look at the free body diagram of the entire structure, we can start from joint A, right? And we can also start from E as well. Both are acceptable here. Okay, so we choose to go with A. Why? Because for A, we only have two unknowns. That is member forces in AC and AB. Okay, so the reason why we've also been talking about we can go with E as well, it is because at E, if you look at there, how many unknowns do you think that we have? Okay, so we have two unknowns, right? That should be member forces in BE and DE. Okay. Okay. So the idea that we shown in our class is that we first go with joint A so that we can solve the member forces in AC and AB, right? Okay, that is a particle equilibrium. Okay, and then we went ahead to solve the joint C. Okay, the reason why after solving joint A, we can solve joint C is because, and you may pause the video and think about that. Okay, it is because that after you solve the joint A, you know the member force in AC, right? So we now only have how many unknowns at C? We only have two unknowns, that is CB and CD here, right? Okay, then is that solvable? Okay, given that for a joint, we need to ensure that we have no more than two unknowns. We have at most two equations, right? So that if you look at C, you only have two unknowns here. Okay, so we can go with the equilibrium C, right? And by solving the equilibrium C, we have the member forces in CB and CD here. Okay, we have the member forces in CB and CD here. Okay, it is good that you can mark those forces that you have already solved out by a correct sign here. Okay, so now we've already solved the member forces in AB, AC, CD, and CB here. Okay, so now what is the next joint that you want to solve? Okay, you may pause the video and think about that. Okay, the answer is that you can go with any of the rest nodes. The reason is because first, if you go with B, now how many unknowns? Originally, there are four unknowns, right? Because there are four truss members connected to that. But two of them, AB, CB, have already been solved. So we have only two unknowns left for B. What about D here? Okay, originally we should have three unknowns at D, but now we've already solved the CD, so we have two unknowns. So for E, at the beginning we've been talking about we can start with E. It originally only have two unknowns. So started from any of those, you can solve that. Okay, so Now, suppose that we go with, okay, suppose that we go with joint D here, okay, because it is pretty typical and has one thing that is pretty important. Go here. Okay, suppose that now we started with now we go with joint D. Okay, now we go with the joint D. Okay, then draw the free body diagram D. Okay, what do we have at D? Okay, if you go to D here and you see that we have member CD, BD, and DE connected to D here. Also remember to check if there's any external force at D. Okay, so by looking at D, we have, okay, we should have all the unknown member forces, right? At D. That is including, okay, that including the member force at C at actually it should be member CD here, right? It should be member CD here. Okay. But do we know member CD here? We know that, right? Because in the previously by solving joint C, we've already have the member CD equals to 50 pound, and it is a compression. Okay, so please note if you've already solved that, you need to include that in your free body diagram. Okay, otherwise you are going to find that there's a too many unknowns. Okay, so at D here, we are going to include the force in member CD, but it's in compression. Okay, now record that if it is compression, should it going towards my point or joint or away from a joint? Okay, so note if it is tension, it should be go away from a joint because it is the bar is pulling my joint. But if it is compression, then it is actually pushing my joint here. Okay, so actually it should be pushing my joint going towards my joint and with the magnitude equals to 50 pound here. Okay, that is a force in member CD. Okay, now what else do we have? We have a force, unknown force BD, and unknown force DE here. Okay, please note we always assume that it is a tension if we don't know that. Now go ahead to list the equations. Okay, we have along x direction and along y direction. And along x direction, we have, okay, we have the two forces in horizontal, since both of them are along the, actually, both of them are going towards the right, which is the positive direction we assume. So they should be positive here, right? Okay. And along y direction, okay, along y direction, we only have FBD here, right? And it have to equals to, equals to 0. Okay. Okay, great. So from here, we can solve. FD is negative 50 pound. Okay, what does this negative sign mean here? It means that the direction of FCD is opposite to what we assumed. We typically assume that it's tension. The negative is compression. Okay, negative is compression. Okay, Then FBD, do we know that? We've already know that it is D0 here. Okay. Okay, FBD is 0. Now we've already solved the D here. Okay. So now I would like to introduce, I would like to have your attention here first. So have you noticed that the force in FBD is pretty special? It is 0. Why? And you may pause the video and think about that. Does that allow does that align with your intuition? Okay. So here's the thing, is that since the 50-pound, which is the force in CD, and the force in DE, they are collinear, right? They are collinear here. Okay, so, and since the two forces are collinear, they can only cancel out what forces here. They can only cancel out the force that on the line, right? Okay, so now I have the third force here, and with no other forces on D. Okay, that means if my force BD here is non-zero, then there's nothing else can cancel that out. In other words, there's nothing nothing else can have y component that opposite to the direction of FDB here. Okay, okay, okay. So this is actually related to very important concept called zero force member here. Okay, so BD, the member BD, its force is 0, and member BD is 0 force member. I'm going to talk about this concept afterwards. And now I would like to introduce, okay, I would like to first introduce a very I would say that it is a pattern here. Okay, if you look at D and the free body, especially, I mean the free body diagram of that. Okay, the free body diagram of that. Okay, isn't it a T shape, right? Okay, so actually here we have the T pattern. T pattern is that if you have a joint, then if you have three forces on the joint here, okay, F1, F2, and you have F3. Okay. Note, if I have F1 and F2, they are collinear. In other words, they are along the same straight line. And F3, I'm sorry here. So M3 is not along the line. Then F3 have to equals to 0. Okay, F3 have to equals to 0 here. Okay, this we can call it T pattern here. Actually, T pattern is a special case to the X pattern that we introduced in the previous class. Because by seeing that there's an X pattern, we see that F1, F2, they are collinear. F3 and F4, they are collinear. Okay, specifically F3 equals to F4 and F1 equals to F2, right? Okay, and in X pattern, if you have F3, I'm sorry, if you have F4 equals to 0, okay, if you have F4 equals 0, isn't it boil down to a T pattern here? Okay, it is, right? That means my F4 equals to 0, and I can directly remove that. And from X pattern, we have F3 equals to F4, but F4 equals 0, then F3 have to equals to 0. Okay, okay. So no matter how, you can understand that it is good. Okay, so basically, it is so the most basic way to understand that is actually equilibrium. Is actually equilibrium. So because along the direction of F1 and F2, the two, according to X pattern, they have to equal to each other here. Because if the particle is in equilibrium, then along the direction, it have to be equilibrium, right? So F1 and F2, they have already canceled each other out. Then we only have F3 left here. since the particle is in equilibrium and nothing else can cancel out F3, then F3 have to equals to 0. Okay, this is a T pattern here. Actually, if in free body diagram, if you see that there's a T pattern, you can always see that's the third force that does not along the same line as the first two forces. They have to be 0 here. Okay. Okay. So lastly, okay, now we've already solved BD and D here. And particularly we know that the member BD, it is 0, right? It is 0 here. Okay. Okay. Now what else do we have here? Okay. What else do you think that we can solve? That we need to solve? Okay, it is look at what else we still should go ahead and solve. It is actually the member B here, right? It is the member B. And which joint we would like to go ahead and solve? Of course, you can go with joint E or joint B here. Okay, you can go with joint E or joint B here. Okay, so actually here, if you go with the joint E, it is simpler. But for the sake of practicing, I would go with joint B, which is actually more challenging here. Okay. Joint B here. Okay, draw the free body diagram of that. And go back what we have. Okay, and so I would encourage you to first take a picture of the structure system here and particularly the dimension, and think about how we can express the directions of the members that connected to B by the dimensions that we have. This is a very important skill. Okay, so think about what are the forces that we have on B. We have, okay, just look at what are the members that connected B. Okay, that is AB, BC, BD, and BE here, right? AB, BC, BD, and BE here. Okay, AB. First, we have AB here. Okay, do we know AB? Do we know AB? And if you look at the solution per size, by solving joint A, we will already have the force AB is 87.5 pound and its tension. So that should be 87.5 pound and its tension. So it is going away from my joint. Okay. We use consistent powder here. Okay. What else here? We should also have member force BC here, right? We should also have member force BC here. And do we know that? Yes. So we know that member force BC, it is actually 106.8 pound and it's compression, right? So it should be, since it is compression, so it should be going towards our way. Okay, it should be going towards. And it is 106.8 pound. Okay. Okay. And do we know the direction? Yes, we know that, right? Because we know that member force BE we know that member force BC is along the member BC here. So if you look at the structure system, okay, so BC is the hypotenuse of a right-angled triangle, right? And the base equals to 3 feet and the head equals to 8 feet. Okay, so you can denote the direction to be base equals to 3 and head equals to 8. Okay. And what else here? It should be member force B, right? We have member force B here. Okay, do we know that? We don't know it. So it is tension. We can assume that it is tension here. Okay. And we can express the direction of the force. Similarly, it is actually by looking at the structure, and we know that the FBE here is along the member BE, and it belongs to a triangle that is a BDE here with the base equals to 4 and height equals to 8. So you should have, okay, base 4, height 8. Okay. Now we can go ahead to draw the free body. We can go ahead to establish the equations. So summation of all forces along x direction equals 0. Okay. Okay, what do we have? What do we have along x direction here? So we have 87.5 pound, but it is negative here, right? It is negative here. And what else do we have here? Okay, we also have the x component of the rest of the two member forces here, right? So it should be okay. Hypotenuse. If we look at a hundred, if we look at a 106.8 pound for force here, and the horizontal component should equals to, okay, it should equals to. We multiply it with. Note that the horizontal component is corresponding to the ratio between the base to the hypotenuse. And regarding the ratio, we have to look at the small triangle here. The base is 3 and the head and the hypotenuse is the summation of the squares of the base and head. Okay, positive or negative here? It should be positive. Okay, similarly, you can have the horizontal component of member force BE here. Okay. And the horizontal component again is the ratio between the base 4 to the hypotenuse. Okay. Those information are from the small triangle that denoting the direction of FB here. That's equals to 0. Okay. And how about y direction here? Okay, regarding y direction, you can similarly have actually now probably you already see that solely based on the first equation, you already can solve that. But if you feel like you are kind of unfamiliar with establishing the equation, I would encourage you to also practice how to establish equations for y direction here. Okay. We have the vertical component of the 106.8 pound that should be for this time it is the ratio between the head 8 to the hypotenuse. Okay, all of those information is from the small triangle that denoting the direction of the force of 106.8 pounds. Okay, going upward. And we also have, okay, so the unknown for the y component of the unknown force, again, it is the ratio between the head to the hypotenuse. Okay, note that it is upward or downward. Now it's downward, right? Okay. It is all the information. So solving either of the equation you are going to have. FE equals to 100, 111.8 pounds. Since it is positive, so it is tension, right? Okay. So far, we've already solved all the member forces here. And this is actually a very typical process of method joints here. When you have a truss structure, okay, method joint is the method that after you solved the unknown support forces, you can go ahead to, okay, repeat the process of particle equilibrium for each of the joint, solving the structure joint by joint, and eventually you will have all the member forces here. And particularly, of course, which joint you should solve first and which joint you should solve afterward. That is a strategy. And I would like to encourage you to imagine that you're playing a battle strategy game, and so your weapons here are actually the two equations for each of the particle, and you can take the unknowns at the enemies. So the rule here is ensure always that you have the number of equations, the number of weapons you have is not greater than is not less than the number of enemies or the number of unknowns here. Okay, that is rule. So based on the rule, you can see which of the joint that you can solve first, and then after you solve the joint, there will be some more joints that you can solve because the reduce the number of unknowns here. Okay, so you are going to repeat the process for all the joints until you solve the all the unknown member forces here. Okay, okay. So what is good for method joints here? So the method joint actually it is a joint by joint scheme. So after what you need to do is after you solve the unknown support forces, you only need to repeat the joint the equilibrium that is actually a particle equilibrium joint by joint. Okay, that is a long process, but for each of the step, that is the basic force analysis. Okay, so eventually it will help you to solve all the unknown member forces here. It is more organized. Okay, okay. So of course, particularly by solving the particle D, we see that there's a force that with the we see that there's a member that with a force equals to 0. This member is called zero force member here. It is called zero force member here. That is an important concept here. Okay. Zero force members here. Okay. So of course, so eventually we actually in the problem solving we identified the zero force member by listing the equilibrium, right? By listing the equilibrium. But actually now I'm going to show you that how we can identify directly by eye observe to find the zero force member in the truss structure so that we can shorten our problem solving. Okay, and also build your sense of the structure engineering. Okay, so there are two rules. So the first rule is that if there are three vectors at one joint and two are coordinate. Okay, if there are three vectors at one joint and two are coordinate, okay, then the third is a zero force member. Okay, and then the third is a zero force member here. Okay, and how to see that? Okay, so if you have a joint here and you have a F1 and you have F2, they are collinear here, and then the F3 should be okay. It should be zero here, right? Okay, that should be that should be there. That should be zero here. Okay. Okay. I'm going to give two additional examples. Here we have F2, F1, F3. Okay. Or we have F1, F2, and F3. Okay. And based on the rule, you may you may try to you may post a video and try to think about which of the members are zero force members here. Okay, okay. So based on the rule, we always so we know that if there are three force vectors at one joint and two of them are collinear, then the third one have to be zero. So we have okay, all the F3s are actually the third are the third y vector here and equals to the there and equals to zero here. In other words, if you establish the equation of equilibrium, F1 and F2 they always cancel each other out. So F3 there's nothing else can cancel that out, and it have to equals to zero here. Okay. In other words, you so if you go back to the problem solving skill, it's problem solving steps for the previous example. Actually, all the examples that we've given here for the rule one, it is actually a T pattern, right? It is actually a T pattern. And for the T pattern here, so the third vector that does not along the line that the rest two vectors are collinear, so the third vector have to equals to zero. Okay, when you see a T pattern, when you see a T pattern here, the force or the member that in addition to the rest two forces or members that has already been collinear have to equals to zero here. Okay, okay. So this is actually our for first rule here. And the second rule. So the second rule here is that if there are two vectors at one joint and are not collinear, okay, so both are zero force members. Okay, both are zero force members here. Okay, so I'm going to give some examples. Okay, and you may look at those examples and